computer is this? Okay, I see.
Yeah, this is the.
Hello, 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 hello. 1, 2, 1, 2, 1, 2.
Can I? Whose
1,
computer is this?
1,
Okay.
1, 2, 1, 2, 1, 2.
Thank you.
1, 2, 1, 2, 1, 2. 1, 2, 1, 2. 1, 2, 1, 2, 1, 2. 1, 2, 1, 2, 1, 2, 1, 2. Yes. Yes, yes, yes. 1, 2. Sorry?
Get free and close gain or what? Or
No, no, you just muted the wrong channels. If you're in aux, then you're.
what? When you change the level, where do you always stay at?
So, you.
What is the channel you change all the faders?
I'm fixing this first. You change the faders on the. You click level, and then you change the faders.
So that is the pre thing that applies to everything.
Yes.
That one is the pre-aux thing. Okay.
Yeah. This one goes.
So basically, if any volunteer looks at the L6, they should always be at the level page.
Yes, yes, yes.
Every time if it's aux one page, it's wrong.
Yeah, they did something bad. Yes.
Okay. And what is the reason that this is fucked?
Yeah. I have no clue. Someone messed with it.
Okay.
1, 2, 1, 2, 1, 2.
But basically basically you're fading all the way to the bottom.
Yeah.
For the fader and then increasing it after the.
I don't know what you mean with that. Hi. Testing. That's not bad. Okay. Testing. Testing.
Okay, hello everyone. Good morning. Welcome to Iwako, your favorite workshop about aliasing capabilities and ownership, I'm sure. It's the 11th edition this year, but it seems that the topic of aliasing is more timely than it has ever been because aliasing has reached the mainstream. And we will see that with in a second with a keynote from Martin, who will talk about capabilities in the context of Scala. Just a few boring logistic details before. We have sort of a packed schedule. We received very interesting contributions. We've also invited a few speakers. So we have two keynotes. One is from Martin, who will talk about capabilities in Scala, and then another in the afternoon will be from James Noble, who will talk about ways to relax trees, I guess, the infamous trees of Rust-like type systems. And the rest will be a mix of contributions that we received and invited speakers. You'll notice that the first session is very Scala heavy. That's on purpose. We joined force with the Scala workshop this year because the lab has been doing, so the lab developing Scala has been doing a lot of work on capabilities, and so we thought that we could just join forces. We also have a roundtable at the end, so please stay for the last session and come with your hot questions and challenges and topics on the issues of ownership and capabilities. We will discuss what we are doing and what we think should be done, where research should go. So please join us. This is not just your regular panel with people saying things you're not interested in. It will be a much more inclusive discussions. And also, we'll have the photographer coming from a little before the keynote of the afternoon. So if you want to be part of the group picture, try to show up slightly before the beginning of the session. Photographer should be here at 1:30, and we'll have a group picture for this year workshop. So with that out of the way, I will stop bothering you with this logistic detail. Please just have fun and let's start. And also, well, on the topic of starting, it's my pleasure to introduce Martin. Martin was my boss for until like a couple of months ago. I just escaped. So of course, Martin is known as creator of Scala, and Scala has been is now leading the charge in the development of capability system using its strong type system, and I think Martin will talk about all of that. So thank you, Martin. I leave the floor to you.
The first question to ask, of course, is, well, why would we be interested in capabilities specifically for Scala? So what is Scala? How would I characterize it? Well, in a nutshell, I would say it's a mostly functional, expressively typed language that combines safety and convenience. That's what it wants to be, anyway. And that mostly functional part is not a compromise. That's exactly how it was designed. The idea was we use functional where it makes sense, and it makes sense in a lot of situations, certainly. And we use imperative where that is simpler or more efficient. But there's a dilemma with these mostly functional languages that Scala shares with other languages in the space, let's say OCaml. The dilemma is that immutable variables and other effects are convenient. It's very easy to just put a print-on statement in the middle of your function to figure out what goes on. It's very easy to just essentially have a side channel where you accumulate something instead of essentially going through a big data structure with a fold and so on. So used responsively, they make code cleaner and more readable and also more performant. But arbitrary side effects, arbitrary global changes, let's say, to the program are certainly not safe. And that's a dilemma because ideally programming languages should guide programmers towards good behavior, towards good coding style. So that ideally a program that looks simple on the surface is also safe and predictable. But with effects, that's not always the case. The simplest and maybe even most readable version is actually not very safe. So using side effects like vars or exceptions can make programs shorter, but also harder to reason about, in particular when we mix it with aliasing. And that's why adding simple direct style effects in Scala is sometimes frowned upon. It's just too easy. It's too easy to do things that might be problematic later on. So that's why often people in the Scala community are outright scared of writing mutable var. That's just not to be done. They jump to great hoops to avoid it, even where it would be harmless. But they have this reputation to be sort of danger territory. So in a sense, Scala programmers, they like their guardrails, and they're faced with the uneasy choice that it could be convenient and fast but unsafe, or safe but complex and slow. And many pick safe and complex and slow, and those that pick convenient and fast, they feel like they have done something bad. So effects are of course a reality. We have them. So how do we tame them? And the popular answer so far is staged effects. So we typically have a pure functional program that constructs an effectful program expressed in a library. The slogan you hear about that is computations are values, and the constructing part is referentially transparent. So most interesting stuff then, the stuff that actually does things, is done in the libraries rather than in the language proper. So libraries like that exist in Scala, like Catsiffact, FS2, Zio, and many others. The downside is that to be fluent in the language, then you needn't know just Scala. That's not enough. You need to know these libraries, which are often an order of magnitude more complicated than the base language itself. So it takes I think it takes quite a short time to learn the basics of Scala, but it takes longer to learn the basics of essentially the type level stack, or Zio, or akka HTTP, or something like that. So if we make a picture of that, then the way we can represent this is to say, well, computers can do lots of things. They have mutable state, they have resources, transactions, errors, networks, everything, communication with the outside world. But we prefer to program in this sandbox in a purely functional way. And then if we want to reach out and do the effects, then that essentially gets mitigated by the fact that what we construct is a stateful program in one of these monad libraries that does these things then for us. So at least in the first stage of programs, we can say, well, everything is functional and referentially transparent. The problem, so here to summarize, what the computers can do everything, and in a program we restrict ourselves consciously to essentially the pure functional subset. The problem with that is it's not so convenient. Typically, this monadic form, it's clunky. It gets worse when you mix several monads, because then you have to go to something like MTL or monad transformers or tagless final and things like that. They're very heavy abstraction patterns that you have to follow to do that, and the code just gets, in my opinion, pretty ugly and pretty dense to understand. The alternative that we are proposing is a capability-based architecture where we say, well, we still have the system, computers can do everything. If we would just let you get at all of these things, we would be back to imperative programming. Let's just use the full capabilities of your computer. We don't do that. We say, well, except in the pure functional subset, everything else, you need a key, a capability to access these things, and that key is given to you typically as a parameter, that somebody passes you the key to say, well, you can use this resource, or you can produce errors in this way, or something like that. So access is controlled by fine-grained capabilities. In a sense, there's not a big deal, not a big difference when it comes to functional programming. In both cases, we have a clear delineation between what is purely functional and what is not. In the first case, that was just the first stage of our program. And here, that would be a function that doesn't take or get any capability from somebody else, is necessarily a pure function. So in both cases, I have a type systematic characterization of what purity is. Another thing that often confuses people is to say the capability version can make non-functional effects safe, but they don't perform the effects themselves. So some people say, well, what, let's say, Cat's effect can do or Zio can do, well, it can suspend your program and do massive concurrency and asynchronicity and things like that. Can you do that with capabilities? And the answer is, well, no. The capabilities is just the key to a possibility to a resource that needs to be in the computer itself. So the runtime needs to be able to do these things. But runtimes are getting better recently. So for instance, if we look at reactive and asynchronous programming, then we now have virtual threads on the JVM, we have continuations in Scala native, and even on the JavaScript platform, we have WASM, which allows essentially JavaScript promise integration, which is sort of a very limited form of stack switching, and there might come more general stack switching is in the works. So we can hope that this will be solved there as well. Okay, so capabilities, what are they? In fact, capabilities are a really old idea. It comes back from 1966 by Jack Dennis and Earl van Horn. And they are just regular program values, but they're restricted in how they can be passed around. So they can be created, they can be passed to other objects and their constructors, and they can be passed to methods and messages. That's all. So the advantages of that is there's no new feature at all. That's just what you can do with normal variables. In fact, what we take away is non-local mutable variables, those you're not supposed to have with these things. So basically, we have a restriction of things, and it's at the same time quite powerful with a proven track record in security. So for instance, if you look at supply-side attacks today, people say the gold standard would be to have essentially enforced capabilities everywhere and do it in hardware because we can't trust our software, unfortunately. So then you have things like Cherry and architectures like that, which give you some hope that you might be able to combat that. So capabilities are the gold standard in security. So why is not everyone using them today? And there are several problems with capabilities. One is, well, to use them, you need a memory-safe language, and that's, of course, already a big jump compared to C, C++, but we are not in that camp. In Scala is of course, memory-safe. But there's still problems. There are other problems. The first is they typically, when you have to pass all these capabilities around, it gets very tedious very quickly because typically you get them from your main program that tells you roughly what the whole program can do, and then you refine them and you pass them on to the leaves where things actually get done. Lots of parameters to pass around, very long call chains. And the other thing is they're actually not, they could also be safer. In particular, there's this problem of capability revocation. Normally, when you give someone a capability, then that entity can hold on to the capability as long as they want. They have it now. They can pass it to others. They can use it. So if you want to say a capability should have a limited lifetime, let's say I give you the capability to perform this operation on behalf of me, and once you're done, you shouldn't have it anymore, then there's really no good way to do that. The way that is proposed in the classical capability literature is basically to equip the capability with a switch that you can turn it off. So basically the one who grants the capability, after the call is done, it turns off the capability, which means that if somebody else wants to reuse the capability later, it's a runtime error. So it's basically a dynamically typed version, but we like static types. We like static guarantees that this wouldn't happen. So the original object capability model is untyped, and a lot of the work has been done in an untyped setting in JavaScript, for instance. Joey was an important language for that. But I believe types can bring important improvements, namely, we can pass capabilities implicitly, we can generate them based on the type, and that makes them a lot more convenient, and we can track what capabilities we have in that type, and that makes them safer. And both of these things work really well for Scala 3 because Scala 3 already has the mechanisms to do that. So Scala 3 has using clauses, which is the modern form of implicit parameters. So it means we can pass capabilities really with very minimal boilerplate. And it has path-dependent types, which means that types can refer to program variables and values and parameters and the like. And that we also need for capabilities, because in the end, a capability is a program value. It's typically a parameter, so we need to be able to talk about that in a type. And interesting. Okay, cool. So so let's talk about how we could model some of these reactive things as effects. So typically effects that we have are I/O, logging, mutation, but there are also control effects like error handling or async, and I want to talk about those. So how can we handle an error handling, which is typically done with an either or something, or a future, which is typically the abstraction for async, in a direct style using capabilities. So let's take a step back and say, well, how do we do error handling in programs? It's a big issue, and people really don't know how to do that. Some propose you should use a sum type, like an option or either, and use pattern matching with that. Pattern matching gets clunky quickly, so how about some types with a for expression, so monadic bind, or exceptions. So composition can be a pain for option and either. Composition with other monads can be a pain if we do monadic bind. And exceptions, the follow-on question should be, well, do you want checked or unchecked exceptions? And depending whom you ask, everybody says, well, yes, of course one or of course the other, but both can be very problematic. What about async, concurrency, reactive programming? Should we have callback futures? Well, that gives you callback hell, we know that. Monadic futures, like we have in Scala, is better, but again, composition with other monads can be a pain. If you want to have a list of futures of an either, then if you want to mix these things up, it gets very complicated very quickly. Async await is an improvement there, so we have this async await macro that does that, but it doesn't work well for higher order functions. Coroutines and virtual threads, yes, but that's imperative. Again, we have access to essentially concurrency and cancellation without putting that in the types. So what I would like to, for errors, is something like Rust's question mark, but a bit more powerful. So here's an example to go from a list of, in this case, results to a result of lists. I have a function all okay. It takes a list of results and gives me a result of lists. And what I say, well, I return a result. So this is result colon, and then I just want to go through my list and map every result I get with the OK function. And that would just give me what's in the result and return it in the list. So some explanations. Result colon, that's just function application in Scala 3. So I can have a function, and I write a colon, and then I put an indented block, and that's the argument. So .OK is like .get, but .get would crash if the enclosing result is an error, whereas .OK would essentially return the error to the enclosing result. And .OK works unlike Rust's question mark. It also works in arguments of higher order functions such as map. So here we see that this .OK is an argument to map, which I couldn't do in Rust. Question mark wouldn't be in a legal place here. Okay, so what about async? What I would like, so here's another example. I want to weight a list of futures. So I have a list of futures that all will give me something in the future at some point. And I want to give you a future of all the results. And if any of the futures fails, I want to give you that failure as soon as it comes. So the way I want to write that is I want to say future of, go through the list and map it with await every future. And that should be all. And again, await should also work in arguments of higher order functions, which our Scala 2 currents async await does not. So the await cannot be in a higher order function, but now here it can. Okay, and await should also be usable outside future blocks. So I should just say, well, even if I don't construct a new future, it should be able to say, well, I have a list of futures and I want to give you a list of the things that are in there, or throw an exception if one of these futures fails. And that should be possible by just writing the same thing, but now I pass essentially a capability to do this. So this async is essentially a thing. Yes, you can do async stuff. You can suspend computation. So that's the capability that allows to await. Okay, so now let's mix these things up. Let's wait. Let's do errors plus async. So here's the thing. We want to await all results. We have a list of futures of results, and we want to give you a future in the future of a result of all the successful outcomes of the parameter futures. Or if any of these fails, we want to give you the error result. So how would I do that? Well, it's really like Lego. I say, well, I need a future, so let me do a future colon. And then I need a result, let me do result colon. And then I need to go through the thing that I'm given, that's an FS. Well, it's a list of futures, let's map that. So what we get is a result, so let's map that with a weight. What we get is a result, let's apply the dot OK for that, and we're done. So this is really like baby code. It's super simple, and this is the same which causes major headaches when you do monad transformers or things like that, where you say, well, if you're not a seasoned category theorist, then you have no hope to do any of this thing. Okay, so what is that? So this is actually quite close to algebraic effects. You can see it if you squint your eyes the right way, you can see there's algebraic effects. So each of these things is a prompt, a future, and result, which essentially represents a handler, and then each of these operations is an effect. So a prompt provides a capability, and an effect uses it. And we just follow the shape of the result type with the prompts. For each constructor in the result type, we give you a prompt that produces values of that result type. Okay, that just looks super simple. Is there a catch? And yeah, well, in fact, it is not that there can be problems. So to experiment with that, let's just turn it around and say, instead of future of result, we now do result of future. We say, well, okay, so we should be able to do the same thing. We have result, future, fs.map, okay, await. Does that make sense? That makes no sense, actually, because we shouldn't be able to break out from an async context, which is this future, to produce a result. Basically, here the result says, well, give me something which is an error or something which is okay. Here, the thing that is okay is a future. You get a future. But in the middle of running this future, I changed my mind and said, actually, no, it's not a future, it's the error. So I can't do that. I have already defined what the result is. Or otherwise put, basically, you would have a control flow that goes out of the future directly into the result, and that's a no-no for futures. Futures have to encapsulate all their control effects in their result. So we want the type system to catch this error, because if we would allow you that, then what's the point of capabilities? And in fact, the type system that we have will give you an error for this. So the 10,000-foot view of this situation is monads don't commute, and that makes them very hard, because if you want to compose monads, then you have to go to more complicated stuff like finite rectangulars or monad transformers. Effects in general don't always commute, but often they do. Capabilities as arguments to functions do commute, so that's always fine, but not all combinations of prompts make sense. So this combination made sense, and this combination didn't. So what we want the type system to flag an error when the prompts are introduced in the wrong order. Okay, and that we use the capabilities for that. So if we take a step back, what capabilities and effects, what their relationship is essentially, instead of having an effect here where I return either error or t, that's a typical effect, I give you just the t, I give you the success case in the case, and I pass as an implicit parameter a capability to raise the effect, in this case to raise an error. So the error goes into the parameter of the function. So why does that matter? Is that just pushing around symbols? It matters because it actually solves a very important problem, which is the effect polymorphism problem. Effect polymorphism problem says that unlike other effects, effects are transitive. So if I have a sequence of functions that call each other, and the last function has an effect, like one of these, then the first function will have the same effect. It has the effect of everything that it calls. And that's not the case for normal types, that you say, essentially anything that I accumulate along the call chain will become my own type. And that means that it's very complicated. If the call graph here is dynamic, like if you have virtual methods or higher order functions, then how do you represent what the effects, possible effects of the first function are? And that's the effect polymorphism problem. So a very simple case, map is always the simplest. Map on a list. So map on a list is written like this in Scala. So if I would write it with effects, like the effects like in Katz effect or things like that, then I would represent the effect as a higher kind of type, f here. I would say my function now is a function from A to f of b, so where f is this unknown effect what I have. It could be IO or either or whatever. And I give you back an f of list of b. And that becomes a lot more scary. And secondly, I noticed that I need to have two maps, map and map f. And that means I need to do that for essentially everything where I can have effects, which is basically everywhere. With capabilities, it's a lot simpler. In fact, with capabilities, nothing changes at all. I have exactly the same signature of map as before. So how can that be? So it can be because now A double arrow B is a type of impure functions that can compute any capability as a free variable. And we also have a type A single arrow B, like what you see here, for pure functions. So pure functions cannot capture any capability. A pure function is a subtype of a double. A single arrow function is a subtype of a fat arrow function. Correct. Yeah. 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 Okay. So in a sense, we waited with Scala to reserve the pure single arrow until we could have pure functions, and that's why Haskell uses single arrows and Scala uses double arrows historically. No, it's just an accident. Okay, you could say good, fine. So this is amazing that you can do this, and the fact it works is that basically the function here captures the effect it can have in this double arrow. It says I come with the effect that I have, and therefore the map function doesn't need to be concerned. The map function will just execute any effects that its argument will execute. So in our terminology, map is actually a pure function. It doesn't have any capabilities by itself, but it might be passed arguments that do have capabilities, and it is allowed to execute them. There's a catch, however, and to look at the catch, we can do a simple example of a try with resource pattern. So we have this program with file. So it takes a body that wants a file and does something and returns a T. And we create a file, a log file, and we pass it to the body, and the body would then use this log file for its logging. And once the body is done, we close it, and we return the result. And the usage would be like this, with file, colon, f arrow, f dot write, okay, right? So we've just passed the function to with file, and the logging is handled by with file itself. Can you see a problem here? Well, the problem could be that body might return a closure, the function itself, that accesses log file after it is closed. So for instance, like here. So we have with file f, and then we pass here the function. That's now an added function to say, well, when the function is called, then let's write I'm late to the function. And that doesn't work, of course, because by the time this thing gets returned, the closure gets returned, the file will be closed. And when we want to write afterwards to that, when we apply the closure, we want to write to the file it's closed. So that would be an error that we have to prevent. And to do that, what we need to do in Scala is we need to add a single letter, which is this up arrow here. So we write up arrow for the file thing, and that would classify the file thing as a capability. We now say, okay, so this thing is a capability, and otherwise with file is as it was. And then if somebody tried the bad thing, the problematic thing, then you would get an error, which is you have to sort of walk through the error message. But the important part here is note that capability f cannot be included in outer capture set S3. So basically, we have a capability that we essentially want to include in this parameter here, and we can't do that. Okay, so the mechanics of how that works is we have these new form of types, which are called capturing types, where T is a type and C1 to Cn is a capture set of capabilities, and these capabilities, they're just regular program values. And the capability, a regular program value is made into a capability because it has a capture set. So every capability gets its authority from some other more sweeping capability that it captures. And there's a root capability cap from which otherwise all others are derived. So that's the way it's set up. And there's a paper later on at Uppsala by Yichen, and he's the speaker on what's in the box. And there's a slight change of perspective in that paper. So cap is now no longer a root capability, but there are several one of them. Basically, each one of them is another existential or universal quantifier. So that's essentially the essence of Yichen's paper on Thursday at Uppsala. But we still write it the same way. So basically, we write the source language the same way, but the foundations underneath are a bit more refined and closer to traditional logic, let's say. So there are abbreviations. So when we write this key hat, that's really just saying it's key hat with cap in the capture set. When we write a function arrow followed by a capture set, that's really the normal function arrow with this capture set at the end. And when we write the double arrow, it's really the arrow with cap. So the double arrow means it's a function that captures an arbitrary unknown capability. Okay, so if we do this in practice, then we can turn it on like this. We have a language import. You have to write import language experimental capture checking, and you then have essentially everything. The separate compilation is supported, and the notational overhead seems to be quite reasonable. So to give you an example of that, here's the list API in our standard library. That's what it looks like. So most functions up here are exactly the same as before. The map function is exactly the same as before, as I've shown you that. In some cases, I need to do a little bit more. So instance, for the flatmap function, I say, well, yeah, okay, so here this function that I pass to flatmap, it can have effects, but so can the iterable ones that I return in the flatmap. So basically, flatmap takes, or let's say concat is the same thing. So I concat an iterable once to this collection, and that iterable can have side effects. As I traverse it, concat can have side effects. So to capture the old behavior where side effects are possible, I can do that by just adding the hat here. And that gives us also a fine-grained control whether arguments should be pure or impure, because I could also drop this thing, or I could have a map, let's say a parallel map with a single arrow, which says, well, to do a parallel map, you have to pass me a pure function. I can't do a function that has side effects. Things get a bit more interesting when you have a lazy collection, like an iterator. So for an iterator, iterators are things where the map would create another iterator that essentially is evaluated only when I call next on the iterator, right? So now this map function would return you an iterator that says this iterator will actually hang on to the current iterator, because next calling on the mapped iterator calls next on the current one, and it will also hang on to the function f, which could have a side effect. So I know very precisely what things are retained in the results of these things as capabilities. So transforms of iterators get capture annotations that tell us about latent effects. And I would argue this is what you want. If you have just an iterator, the next question should be, well, an iterator here, but it can do what? Right? So you want to know what it can do, and here that it does precisely that. So basically the annotations stay out of your way when they would be trivial, and they tell you precisely what you want to know when they're not trivial. Okay. Sorry, I did. Okay, so that was the current state. No, so the current state is that the library that I've shown you will actually ship. It is in the nightlies. standard library is now fully capture checked, so you have the annotations in the library, and we are also about to release capture checked versions of other things which are not yet in the standard library. One is steps, which is an incubator for a set of utilities such as result that I've shown you, and the other is gears, which is our concurrent programming with direct styles, futures, and channels library. Okay, so what are we cooking now that we're done with this? So the next steps is that we have seen that capabilities are, so far we have seen that capabilities are resources with limited lifetimes, but they can also do more. And another question is, can they enforce sharing restrictions? So what we want to do is exclude global side effects, avoid data races, fearless concurrency. That means we want to have capabilities that mediate access to immutable data structures. And that's another project, or sub-project that we started. It's called Project Capybara, Capabilities for Mutation. Capybara is because they're nice animals, and also if you pronounce it the right way, so it's sort of capybara, so borrowing this sort of thing. So anyway, so that's the new project. This thing was ChatGPT generated after some input so from the oldest Western depiction of a capybara, which is here. So it's the banana becomes the lambda, and the palm tree becomes the Scala thing. So I give you just a quick run of what this is. So here's a matrix multiply, matrix A, B, C. The question is, what is input, what is output, which arguments can be shared, which arguments are unique. It doesn't really tell you much, right? So this sort of thing, but that's sort of the things you have to contend when you have operations like that. So what we can do now is we can have first define a matrix to be mutable. So a matrix extends mutable. And then furthermore, we define the method that sets an element of the matrix to be an update method. So that's two things. And then in the mutation, what we do is we give you the output with a hat. So that says this thing is writable, and these things, A and B, are only readable. So the hat now means it can be modified. It's a capability allowing an effect. And the way the fact that we interpret it as that has to do with the fact that it's on a matrix and matrix is mutable. So if a capability is on a matrix and matrix is mutable, it means it's mutation. And it also means it doesn't share with anything else that can be accessed, and that's the separation part. So with the separation checking that we have, we can now say that if we multiply matrices A, B, and C, that's okay. But if we multiply A, B, B, that's not okay, because B cannot essentially has a hat here and cannot be referenced separately. On the other hand, multiplying A into C is okay, because the first parameters here, they're just passed as normal parameters. And that requires currently a separate language import for separation checking, because that's work in progress and not everything is checked out yet. And what we also have is we can do that for linearity. So Scala has these buffers, and buffers has this plus equals method. And plus equals is sort of like concatenation, but it's imperative. And we want to protect ourselves better against side effect of these things. So an example here would be we create a buffer and we append some elements to it. And the result is a new buffer C. And now we append a further element to C. And but now the last one should be an error, because we append something to the original buffer, but the original buffer is now aliased in first C and then D. So appending something to the original buffer would have a hidden side effect on these things here, because they all share the same buffer. There's no copying here. So what we want, what we're after, is a linear type system, and that's enforced by this consume thing. We can put consume on a def or on a parameter, and that means once we've used it, then it's no longer available. So if we put it on a def, it means that the receiver is no longer available. So here, the B plus equal would be consumed, and that means we can't use the consume afterwards. So to conclude, capabilities are super versatile because they can model global effects, control effects, permissions, mutations, information flow. The list goes on. It's really a Swiss Army knife of things in software security and trustworthy computing. The main value proposition of Scala is to be both safe and convenient, and I think with the right types we can make capabilities safe and convenient. We can use implicit parameters. We are using clauses and capture sets to model the retained capabilities. So to find out more, there's a paper in ACM Toplas 2024 that we saw the foundational paper on this. It's called Capturing Types. There was a paper at UPSLab about our first steps into separation, which is not what you've seen. That was like a preliminary thing. And there's a paper at this UPSLab on what's in the box about essentially the current calculus that underlies our system. And there's an implementation in 3.8, which is due later this month. If you look at DOCI, EPFL, docs reference, you already get the documentation of the current nightly versions, and that's probably the best place to start with if you want to play with it. Thank you.
All right, I think we have time for a few questions.
Just curious, is Scala the first language to combine capabilities and effects like that? And how does it compare if there are others doing similar things?
In general, yes. In general, I think it's the first, well, I'm not sure about small research languages, but the first sort of language in actual use that does this, I believe, yeah.
Okay.
Yeah. History in typing, 25 years, I would say. And essentially, the meaning here is capability is another layer of our type system, but they are essentially types only, sort of like regions or things like that. And I think reference capabilities are of this thing. It's a type systematic abstraction. Here, our capabilities are really regular program values. So in a sense, they are more direct and more easily to understand and to manipulate because you have the full power of the term language for them. That said, there are also some tweaks where object capabilities are a problem. For instance, the way I presented them, they're always real program values. So they get passed, they take up space, they take up time to pass them, and you don't need that always. So we have another thing which is in the next talk after this one about how we can have erased things, and then they become more like reference capabilities. So they're object capabilities, but we have an erased modifier that says these things are not present at runtime. So and there's a type system that checks that that's possible.
Yeah, but maybe we can keep the question for after because we are running late. Yeah, I'm sure Martin will be available at dinner and maybe at the later session today. So speaking of Capybara, which was the future, then we have the future being presented to us by Yi-Chen. So Yi-Chen, take it away.
Okay, thank you. And yeah, so Martin already talked about Capybara, and today I'm doing a short demo of Capybara using a experimental compiler which implements the type system we are currently formalizing. And so what is a capybara? So apparently it is a cute animal, and they are actually in Singapore Zoo. And so if you like capybara too, you could go and see them. So and this picture is shot by Wen Hao. So yeah. And what is system capybara? So it is actually a type system based on Kepler's, which is the system I'm going to present on Thursday on UPSLA. And it's based on capture checking, and it makes use of capture checking or it extends capture checking to reason about separation and freshness. And maybe let's first look at what is a capturing type. So it's a really, really quick introduction that capturing types, the core idea of capture checking is to track captured variables in types. And to do that, we augment types with the capture set, as you see here, which is like the capability a value can capture of this type. So we can look at some examples actually. So now we have, this is like in that small experimental language, and now we are using this scoped capability pattern, which Martin showed just now also, which we say, now I have console capability locally, and I can use it to print things to console. And now if you have a function that uses that capability, what we will get, you will return, okay. Yeah, you will, let's look at what type it has. So it has this type, which says this grid is a function from unit to unit, and it's capturing console, the capability. And it's like basically saying that I'm a function that will perform console I/O. So that's the key idea of capture checking. And if we ever try to like pretend this to be pure, of course we get an error. Like okay, should be like this. Yeah, so we say we are pretending it to be pure, so this is like a pure arrow, and we are asserting it is capturing nothing, and we are actually using some effects, and of course the compiler will not be happy about that. And now maybe let's have some general idea of separation and freshness. So it's basically a aliasing controlling problem. So for instance, like if we want to run OP1 and OP2 in parallel, and we want to ensure data rates freedom, and what matters is what OP1 and OP2 accesses, or like what aliases are OP1 or OP2, or what references OP1 and OP2 is referencing. And if they are both reading from some mutable state A, it's fine. But if that's another case, like if someone's reading and the other is writing, or both are writing, then no, it's a data race problem. And to detect this, what matters is what OP1 and OP2 accesses. And similarly, if we want to have the resource pattern that, let's say F is a file, and we first close it, and then we are running some operation that access that file, then it should also be a problem, because then we are basically accessing a closed file. So all these patterns, capturing types can help, because we are essentially reading about the captured variables of these closures and operations and values. So if, like here, OP1 or OP2, if it access A, or if there's some OP access F, then it will somehow be present in the capture set, in the type of these values. So then we can make use of this information in the type system to prevent these bad accesses, to reason about these separation and freshness properties statically. So now let's see. So Capybara is based on this general idea. So we are in capture checking, and we have some aliasing information, we have some reference information, and now we make use of this information in the type system to reason about separation and freshness. And how do we do that? So the first step of Capybara is to qualifying capabilities with access modes, which you will see here. So basically we are adding another M, which will not be present in the service language of Scala, of course, because we do some inference. But in theory, we have this access mode on capturing types. So it can either be maybe read-only, or like it is owned, or something like that. And we can again see this in action, that, yeah. So here we are defining some mutable capability, you can understand it as like a mutable capability, which is a reference that's holding a mutable data of I32. And here you can say I only want the read-only mode of a reference, and I'm just reading from it. And if like here, if we have an F that reads from capability A, then it will be, of course, only capturing read-only A. So apart from qualifying the types with access modes, we can also qualify the capabilities, which represents how the capability references, which represents how these capabilities are used with these modes. And now we know that F is only reading from A. And if now we do par, which is some hypothetical library function, which runs two functions in parallel, you will see that it will pass, of course, because both are only reading from A. And if here, if we only have a read-only reference of X in this read function, and if we ever try to write to it, of course, our system will not be happy because we are expecting a mutable reference, but we got a read-only one. So, the general idea of this is that in the type, the access mode in the type represents the permissions, the authorities you get from this type, and the access mode on the capability references means like the price you have to pay for running this operation. So it's like F will pay the price of read from A, and to do that, and to if you have another function that is just writing from writing to a reference, and maybe let's comment this out for better readability, and okay. And you will get another capture set of this function, which is like G, which is capturing A. And it says that G is actually writing, it can write to A. So it has to also pay the price of writing to A, so it cannot possibly be run in parallel with G itself or F. Both will be an error. Like here, we get a separation error because G and G, they are both writing to A, which is apparently shouldn't be allowed. So yeah, and this is the first step of this idea of using capture checking to reason about separation. And then with this read modes, we already see that we can reason about, like, we can prevent some sort of data race freedom. And now I can show you more examples of reading about separation reasoning in this calculus. Sep check. Okay. Yeah. So let's say again, if you saw Dimi's talk yesterday, we have this swap example, which we want A and B to be separated, and like if here you have two references A and B, and as Martin mentioned just now, we have some fresh roots of capabilities. So this means that we are replacing cap with existential captures, and this is an example of this, that we say if you create a new reference, then you are getting a new fresh capability which is separate from the rest of the world. And that's why here swap A and B is allowed. So you can do that because A and B, they are separated. But if you do a swap A and A, it will of course be an error. And if you put A into an alias, like T1 is an alias of A, and you swap A with T1, would that work? Of course not, because we see that our system can make use of the capturing information to know that T1 is actually a reference of A, like we see here, like the type of T1 is the ref of A. So we know that T1 is just an alias. And now the next step is freshness. 5 minutes, okay, yeah, freshness. So let's see that. So yeah, I have some example of some example API. So it's not doing anything. It's just to show our type system. We have an open file, which is opening a file for us, open a new file handle for us. And we can read from it, we can write to it, and we can close it, of course. So if we do this, read file F, it will work, of course, and it will work. And if now we close it, close F, which we see here we have consume, which in our system means that we are like dropping this capability and preventing it from being further used. And we write file or read file again. It will be a consume error. And similarly, if you have an OP that reads the file, and if you want to call this OP after you have closed this file, then it will similarly be a consume error because with capture checking, these aliases are all in the type system. We can reason about them.
In line 12, is the string hat in the result intentional?
Yes, it is intentional, because in string in this demo language is represented as array, and the array is tracked. So okay, yeah. Actually, I have another thing. So actually, with consume, we can model affine functions too. Here, if we have this round once, which says it is consume itself, then it can only be round once, of course. And if you try to write twice, it will be an error. So with consume, we can actually model this affine thingy. And finally, so we have the formal system, which has informed and inspired the development of this demo compiler, and also the separation checking implementation in Scala 3. And it is based on Kepler's, and I'm going to present it on Thursday in the morning. And thank Martin for talking about the essence of this work. I think it already covers what I want to say. And please come if you are interested. And in the end, thank you very much for this, for being here and listening. So now we are developing the system, and it reasons about separation and freshness, and the current developments are like the formal calculus that is formalizing these ideas, and we hope to establish some connection into separation logic. Therefore, we want to do some semantic type soundness. And maybe we can encode Rust in Capybara because we can reason about these things, and maybe we can have a type system for Rust that is much better than Oxide or featherweight Rust. And and we have a prototype implementation of the core type system. So, and also experimental separation checker in Scala 3. So if you are interested, you can scan this QR code, which will bring you to a project page of Capybara. And we also have a project page for capture checking in general, which is just couplers.cc. So if you are interested, you can check them out. And do I still have time? Okay, yeah, because we still have time, I can show a final example. Which is the array buffer thing that Martin has mentioned, but it's done a bit differently. So I have this string buffer, and this code is actually working, so it's actually implemented, and we have some APIs for this buffer, which we say we can append to it, and we can get the result of it. so appending to it will not consume it. It's like modifying the stream buffer. And if you retrieve the result of it, and like it's the string you are building, then it's like you are finalizing this string builder, and you should not use it any further. And now we can actually do that. So like if we compile this code and if we run it, it will show hello world, which is what we've done here. And if we want to append the string after we have got the result, after we have finalized the string buffer, of course, we will get an error. And similarly, we can't bypass the system via some aliasing. So it will always be detected. And yeah, I think that's all. And thank you all for listening.
Thank you very much, Xinchen. We have time for one quick question, maybe?
How do you handle functions which kind of alias themselves? So a function which, say, takes a ref that you defined and returns a reference from the result?
A function that reference itself?
No, so like you had that example with ref, right, that had an integer inside of it.
You mean like...
I guess the second one, the third one.
Yeah, second one.
So if, say, you had a function which took a ref and returned a ref, like as an argument, and then returned it as a result.
Yeah, so it will, so if you write it like that, it will be failing because it's essentially like hiding the aliasing. Like
exactly.
you are forgetting the aliasing. Okay, yes. Oops, let me comment this out. Yeah, so now it will say that we are treating this capability X as fresh, which is the case here, but it's not actually fresh. And to make it work, you must consume it, because that will make it actually fresh. Like it will prevent X from being further used, and okay, yeah, it works. It will prevent X from being further used, and it can be treated as fresh. And internally, or like in the theory, we have this thing. So this returned fresh thing is modeled with a existential. And we say to actually introduce an existential, you have to ensure that the thing, the witness, is fresh. And to do that, you either consume it or you actually is creating some fresh things. Yeah, you be explicit. That will also work. Yeah, because then it's not existential, it's a normal capturing type, and it's just preserving the alias.
And I guess a quick follow-up, do you support then also if I have references inside of some other structure? So if I had this ref in a tuple, let's say I took a tuple of two refs.
Yeah, we can do that, like a ref pair, maybe just P, because A ref hat, B ref hat, and we can say we want to make P. So we can do it like this.
Maybe the same signature that you had before, where it takes a P and returns one of the references from the P.
Yeah, okay. We can do this too.
Let's say I return the first tuple of the first element, so like a ref.
Yeah, ref P dot A.
Okay. We're pretty pressed for time. Maybe we can make this demo over the lunch or.
It's not working. Okay, but I think this will work. Sorry, this is a bit buggy, but
yeah, it's okay. I mean, I just wanted to see how
this works.
And if it works.
And
Thanks,
if you okay.
Okay. Thank you very much, Etienne.
Thank you.